first speaker then was a chap called Harry Foster. Harry's been back once, but he's come back this year as well, just for Verification Futures. So we're very happy to have Harry from the States. Harry is from Mentor, a Siemens business. He is the chief scientist in verification for Mentor, and is co-founder and executive editor for Verification Academy. He holds multiple patents and has co-authored 6 books on verification. Harry was recipient of the Accelera Technical Excellence Award and was the original creator of the Accelera Open Verification Library, OVL, which I happened to use a while ago now. So over to Harry. Thanks, Harry.
Thank you, Mike. Thank you. Yeah, I'm actually very proud about the co-founders and executive editor of Verification Academy. I want to share with you a couple, some data on that. It's interesting. You can see that we're approaching close to 60,000 members today. We're still growing at roughly a 17.5% compounded annual growth rate within the last 4 or 5 years. So this is something I'm very proud of. If you're not familiar with this, the Verification Academy consists of video courses. In fact, we just released a brand new one on portable test and simulus PSS standard. A whole set of verification cookbook, discussion forums, pattern libraries, on-demand seminars. At DAC this year, we had a booth at Verification Academy. And all those are recorded. Those are technical talks. You can go out and see them on demand out there. So again, verificationacademy.com. This is a free resource that's available to you. So getting back to my talk, let me mention the title is a long mouthful. I this year was asked to be the technical program chair at DAC, and this was one of the hardest things I have to admit I've ever done. We had 815 research papers submitted, and I was swamped. So I got invited to come give this talk. I said, sure, but I don't have time for the title. Here's what I want to talk about. So a colleague of mine came up with the title, and this is not what I would have picked. So what would have I picked? I would have picked hammers, nails, and bullets. And by the way, okay, so I do live in Texas, and I don't drive trucks, and I don't have guns, but you'll see where I'm headed with this in just a second. Hammers, nails, and bullets. First thing I want to talk about is industry costs. Some of you might know I do industry studies every 2 years. And I'm going to share a little bit of data with you today, not go in depth like I normally do, but kind of a pause where we are in the industry. The first thing that we track for many years is the number of required experience, obviously cases. And traditionally spend around 30%. We're able to achieve first silicon success, and it spreads out from there. You can see that in 2000, sorry, we seem to have lost our, over here, the green color represents 2018, the last study. So we've actually got worse this past, in this past study. But it turns out that it is not due to functional flaws. In fact, we've actually have improved in functional flaws. I'll point to details later in the study. I'll point to details later in the study. The reason we've had this decline, the reason we've had this decline in terms of success or predominantly due to timing as well as noise. We've improved in terms of functional flaws. Now, what's frustrated me over the years is that we have this kind of a metric in terms of how good are we doing as an industry in verification or in validation. We've never had anything similar in terms of FPGAs. So 2 studies ago, started asking the question, did you have a non-trivial bug escape in production? And this is pretty remarkable. 84% of FPGA designs have non-trivial bug escapes in production. Okay? Now, the reason this is significant, there's some market segments, such as mirror, that the cost of removing the cover to go fix the FPGA is astronomical, because I got to go revalidate the entire system. We have a long ways to go to address this. But let me get back to the hammers and nails. And hammers and nails, I think, in terms of what is our most used technology for verification, it's obviously simulation. It always will be, always has been. And here's some data where we're standing today in terms of building test benches. And you can see that, we're saturating in terms of system Verilog. Everything else is roughly flat. And let me comment, this is worldwide data. If you look at certain regions of the world, certain market segments, you can see slightly different. But I'm tracking this across the world to kind of see, is there any type trends? We have matured and we saturated in terms of basic. FPGAs is a little different. And I have data on that all referenced later. Here's where we are in terms of methodologies. Again, we're levering out in the lower 70% adoption of UVM. And again, this is based on worldwide aggregated data. Okay, so simulation techniques. Here's some other simulation techniques. And what's interesting about this, and I apologize, we've lost our legend again, but the first dark color is 2007, the purple color is 2012, and the dark green is 2018. You can clearly see that the industry matured its processes during this period. What is real interesting, if you went back to 2000 to mid-2000 timeframe, the ASIC industry was caught off guard with growing complexity of SoCs. Really caught off guard, and then they were forced to mature the processes. Sure enough, we're basically saturating adoption of these different techniques, simulation-based techniques. The FPGA market is going through the same struggle at the moment. It's growing complexity FPGAs, moving to very complex SoC class FPGAs. They're being forced to mature their market in that. Okay, so these are the hammers and nails in terms of simulation be the predominant techniques. However, I'm sure you've heard this quote, if all you have is a hammer in the toolbox, everything looks like a nail. So let's talk about where this starts to fall apart. First thing I'm going to look at is that this is fairly typical SOC verification flow. You might have variations on this. Typically, you start to have unit testing with simulation. The goal, by the way, of the way this thing is structured is to minimize the debugging time. For example, if I'm doing some sort of bare metal or performance type of testing, I don't want to find a connectivity issue. So I do these in stages to find my bugs as soon as possible is the goal. What we've moved to basically is software-driven verification, and again, I've lost some colors on this, but basically from my functional scenarios above, I now am working in software-driven verification, and traditional simulation approaches start to fall apart. I can't get enough cycles, obviously. So, and this kind of represents the various engines and the performance of various engines. And this is just kind of a ballpark. The reason is, for example, there are cases where actually can use formal and system validation, even in post-silicon validation. But this just kind of gives a ballpark where they're most effective. Okay. So what about silver bullets? Well, folklore, common folklore is that if you take a bullet, cast a bullet in silver, that it is one of the few things that's effective at killing a werewolf, And it's also a metaphor to mean that it's a magical solution that will solve everything. In verification, obviously, there is no silver bullet. But I could make a claim that there is a silver bullet if it's applied narrowly focused to a specific problem. There are silver bullets in those particular areas. For example, let's say that I have a hypervisor OS controlled power management. Now the hammers and nail would be, let's do RTL simulation with the software. Oh, my Apple Watch can't give me the answer to that. But so Siri always comes in at the wrong times. Always, yeah. But anyway, so RTL simulation with UPF and software and everything would not be effective in this case. I just can't get enough cycles. Emulation is a much better solution. Again, narrowly focused for this type problem. Another example would be, for example, metastability. There's a class of bugs that cannot be demonstrated on our RTL model due to metastability. And so gate level simulation would potentially do it, assuming I could get enough coverage and I get enough time. But this illustrates the hammers and nails versus the silver bullets in terms of CDC solutions. My point being is that you can take a narrowly focused problem and create a solution what you could classify as a silver bullet. Okay, so what about planning formal into the flow? Now here I'm going to talk about formal property checking predominantly and give you a little bit of data. Here's where we are in terms of formal technology adoptions. We're approaching roughly 35% in terms of ASIC. That's 35% of projects out there have adopted formal property checking. We've had, and this is in ASICs, and then the formal apps were about 9%. This does not include CDC, and this includes all the other formal apps. We've had some fairly significant growth in terms of CAGRs in FPGAs. Again, to my point earlier, is that the FPGA market is being caught off guard, and they're ramping up adoption of many different techniques to address growing complexity of SOC class FPGAs. This just illustrates some of the formal apps. We talked about connectivity as being one of them. That's just one example of formal apps if you're not familiar. But my talk today is actually on formal property checking, some of the challenges of adopting formal property checking. And typically what I find failure in the industry in adopting this is a failure to plan. The first thing I want to talk about is formal use models. And here I want to put up this notion, two different types of use models. This was presented by a colleague of mine. I was on a panel at DAC in 2003, and he put this graph up, and I love this. He's illustrating two different use models. One is bug hunting, and the other is assurance. Okay, and so if you think about bug hunting in terms of success, here you might have many assertions, and the goal is to drive the bugs down as quickly as possible in terms of productivity focus. If I run into any challenges or complexity, I move on. I am not trying to actually formally prove this in terms of a quality focus, but the goal is to drive the bugs down as quickly as possible. Assurance, on the other hand, I have one comprehensive spec, and the success is measured in terms of design meet the spec, and again, it's quality focus. Assurance takes a significant amount more experience to actually achieve this. And one of the key points is formal test planning. So I'm going to share with you my 7 steps to formal test planning. I've written papers on this in the past, and without proper planning, very few people were able to achieve assurance, is my claim. Okay. The first step is I find a lot of people don't understand appropriately how to identify candidates that are appropriate for formal. And so first step is identify good candidates. This is an example of a candidate that's not a good candidate for formal. You can think of this as a block that is sequential in nature. I have data coming in, maybe going through some sort of complex math transformation and then flowing out. Examples of that would be like convolution unit and MPEG decoders, any of these types of floating point, any of these types of data flowing in, complex transformation and going out. Okay, this is not a good candidate for formal property checking. On the other hand, a good candidate would be designs that are concurrent in nature, they have multiple data streams or multiple interacting state machines. Examples of this would be like these complex interfaces, PCI Express, any sort of DMA controllers, and so on and so on. Okay. So that's our first step. We identify what's a good candidate, what's not a good candidate. The second step is that we then describe the block that we're going to verify. The goal here is there's multiple stakeholders involved in this. Quite often somebody verifying it as well as a designer. I find very few designs nowadays actually have microarchitectures. So how many people are working on design that have microarchitecture? Back in the old days, yes, back in the old days we did, and this was well known so that you could actually understand the block in detail in terms of what you're going to verify. Our goal is not to create a micro architecture, but at least capture what it is we're going to verify so when we have these discussions. You know, it can be simple block diagrams and waveforms and so on. The third step is then to document the interfaces. And you can't really see this very clear. Hopefully it's better in the printout. But the idea is that I basically have a table. I'm listing the signals and the description of the signals. The reason this is important is that this is used for my assumptions as well as my properties that I'm going to create on the design. And then the next step is to capture the properties. The mistake I find a lot of people do is that they jump into creating system Verilog assertions, PSL, whatever, without actually capturing the properties in English. Oh, let me share a story. I was in Japan giving a talk like this a couple of years ago. And I said, okay, the first thing you got to do is sit down and you need to write your properties in English. And they all stopped and looked at me like, oh, this is going to be a lot harder than I thought, you know. So I should say capture your properties in a natural language, you know. But that's a very important step. And again, there's a tendency people want to start writing assertions, and it's just too soon. After you have the properties captured, then in a natural language, then you can formalize them into, you know, whatever your favorite type of assertion language. Here's an example of system Verilog assertions. Then define metrics, and so we can measure success in this. And by the way, so this in itself is a talk, and I don't have time to go into that today. But I want to mention out on the Verification Academy, we do have a whole course consisting of 5 video recordings that talk about how to create formal coverage. Our goal here is to determine, you know, did we over-constrain the design to help us measure interesting corner cases using as we actually go through the formal proofs. Okay. So anyway, if you're interested in learning more how to do this, there's courses out on Verification Academy. And then finally, we select our strategy. Now, here I recommend people take their list of properties and then order the list. And the way I do this is I basically ask the team, did you have a respin on previously on similar type property? If so, you might want to actually bump that property up higher on the list. Are you concerned about achieving high coverage? If not, you might want to bump that down on the list. You know, is this some sort of new type of control and intensive logic? Do you have sufficient resources to the design team? And this is actually a very important one. For example, if you're handed a block that you no longer have the designers available, you might want to skip and go work on a different block because your chances become a lot more complex. You know, so my goal is I'm trying to order the list because I can't do everything to get the highest return on investment. Then I essentially draw a line based through experience. So these are the ones we're actually going to go after. The other set, if we have time, we'll go after it. All right, so that's one step. And then we figure out the strategy on this. And our strategy is, for example, are we going to do an exhaustive proof on this, or we're going to go bug hunting on these? It's a decision we try to make. We're trying to improve interface compliance. We're trying to improve coverage. These are certain decisions. Let me mention, if I am going for assurance and a complete proof on certain blocks, it requires skills that are way beyond just the tools. And we also have a course on the Academy that's an advanced course on how to do abstractions, how to do different techniques with the assumed guarantee. Without these techniques and these skills, you can't achieve exhaustive proof on a set of certain types of blocks. Now, I mentioned there's a class of blocks that are good candidates and a class of blocks that are not so good candidates for formal. What I didn't mention was what's easy and what's hard. Okay, and that should be considered too. And I have put together a list here of fairly common type of design blocks and put over here the list in terms of difficulty level. So if you're new to formal and haven't done this in the past, I would recommend you start with these easier ones. The reason is when you get down to these harder ones, it does not matter what tool you use in the market. This requires skills in terms of introducing abstractions, how you're going to partition into a SIM guarantee, lots of different techniques that if you don't have those skills, you won't succeed. And by the way, I use the analogy here. If I came into you and say, I've got this amazing tool that can do constrained, random, coverage-driven verification, here, go at it, would you succeed? The answer is no if you've never had any experience with object-oriented programming or how to create coverage models until you build those skills. You can succeed in these very difficult type blocks once you develop the skills, but skills are required in the... So, boy, you should hear my wife. She just goes crazy over Siri. You know, she never answers my wife's questions. But anyway, so that's something to keep in mind is as you're getting into this. The planning part of it is what's a skill level within the organization and how to build that skill level up to actually achieve these very complex type of properties. Now, I want to leave you with a couple thoughts. One is I talked about planning being very important in all aspects of verification, understanding the strengths and weaknesses of the different techniques. And formal can be a silver bullet when applied narrowly in certain applications, and that's where the formal apps come in. If you want to do formal property checking, if you don't plan it, I guarantee you will not succeed. You will not get high return on investment for doing that. It's critical you understand when to and when not to apply formal for success. And again, there's a lot of free training we offer out on the Academy. Now, on my industry studies, if you want data on our 2018 Wilson Research Group study, I have a recorded version. It takes about an hour to view the entire study. It covers both ASICs and FPGAs. You can find that out there on the Verification Academy. I've also created a 15-part detailed blog series that's out on the Verification Horizon blog series. And then again, Verification Academy to build skills. If you have any questions about our formal solutions, we have a whole mentor team here someplace in the other room. With that, I have a few minutes.
You have time for questions, actually. Yeah, you have time for questions. 5 minutes. I have a quick question. One question that always comes up for me with formal is how do you integrate those coverage metrics with simulation coverage metrics?
How do you integrate the formal coverage metrics?
Yeah, formal and simulation.
Yeah.
How do you bring those two
technologies
together?
Well, first of all, we're dealing with two different domains. One, we're basically the simulation domain. We're dealing with the input space. We're dealing. Did I actually create stimulus or activate a structure or a line of code in the design? It has nothing to do. Did we observe it, right? Yeah. So they're actually two different. And formal we're dealing with state spaces, you know. Okay. So they're actually two different domains. However, what we can do is, in terms of the requirements that we're checking, those are obvious in terms of did I have functional coverage for that? I can measure my functional coverage and formal too.
Okay, so you combine them at the requirements.
Yep.
Coverage level. Okay.
Yep.
Okay. All right. Okay, that's a question. Just give me a minute to get there.
Hi, Gareth Edwards, Xilinx. We, as the FPGA company, have had a hard enough time getting our customers to do simulation instead of going to the lab. How are we going to get them to do formal?
So, make sure I understand the question is that, so basic organization, a very simulation center, which again, simulation is the center of the universe, and it will be in verification. How do you get the team to do formal was the question?
No, it's not my team, it's my customers. You know,
your customers.
We're an FPGA company.
Yeah.
We have been encouraging our customers to do simulation. We had a hard time getting that to happen. Now we're having the same conversations with our customers about formal. Yeah. Yeah. And that's going to be the same struggle again, I think. Okay, well, so in terms of formal, to get your customers, particularly we saw maturing of the FPGA space, it is happening in adoption of the apps as well as formal property checking.
I have not seen too many organizations, whether it's ASICs or FPGA, succeed at formal property checking unless they have a dedicated team, okay, for formal property checking. Now, the formal apps is different, and I think that would be your best chance for your customers because it does not require a lot of skills. It doesn't even require skills in how to write assertions. You know, so it's kind of like first you've got to crawl, walk, and run. My advice was guide them in those formal apps because they can get a lot of value out of that without putting a lot of effort into it, and then build skills where then they can move on to formal property checking.
By the way, I remember using formal verification in software back in the 80s, and I think software has the same problem as hardware, getting people to use formal. One of the companies I'm working at, actually, they put it in the hands of designers. Designers find it very useful to write assertions as they go and then visualize those assertions and then try to prove some of the assertions.
Yeah, the issue I have with that is that today a lot of designers today have to wear many hats, right? And they're working over a project for a year. To master any one tool is very difficult. And for example, they got to do synthesis, timing analysis, blah, blah, blah. And then, okay, here's formal property checking. These formal apps, yeah, I can see that. But the massive formal property checking, it takes skills, and you see less and less success with somebody wearing multiple hats actually do.
No, I agree. It's designers with the biggest brains that tend to adopt it, from what I've observed. A full recommendation to look at the Harry's surveys as well. I've been watching Harry's surveys. The first one was 2006, 2007? 2007. Yeah, and they're fascinating. You can see the way our industry changes, and the adoption of UVM and System Verilog has been staggering, and hopefully we'll see that with formal as time goes on as well. So a big thank you to Harry. Thank you, Harry.